In the beginning, humankind was enveloped in the illusion of a still, unchanging universe. The skies overhead, with their timeless constellations and steady movements of the planets, gave the impression of a cosmic order, a grand, eternal painting stretching across the heavens. To our ancestors, the earth was the pivot of existence, immovable and constant, while the stars and planets danced around us in a celestial waltz orchestrated by the divine. This vision of the universe held sway for millennia. The constellations stayed the same, the moon's journey was predictable, and even the planets followed their paths, seemingly as orderly as clockwork. The earth was the center, a solid, permanent fixture in a vast, eternal cosmos. Our ancestors, from the ancient Greeks to the Mayans, saw the stars not as distant suns, but as fixed points in a grand cosmic design. But there came a moment, a crack in the fabric of this illusion. It started with the work of Copernicus, who dared to suggest that the Earth was not the center of the universe. His proposal, though revolutionary, was not immediately accepted. Then came Galileo, who, armed with a telescope, saw moons orbiting Jupiter, proof that not everything orbited Earth. Yet, it was Johannes Kepler, whose mathematical analysis of planetary motion, coupled with the discovery that planets followed elliptical orbits, that fundamentally shattered the old world view. The stillness was gone. The universe was far more dynamic, more complex than anyone had imagined. We now understand that the universe is anything but static. It is in constant motion, a dance of unimaginable proportions. Not just the stars, but galaxies, superclusters, and even the very fabric of space itself is in constant motion. The Earth spins, the Sun orbits the center of the Milky Way, and our galaxy moves through space, all while being pulled by forces we cannot directly observe. Yet, even with all this motion, we don't feel it. The ground beneath our feet doesn't tremble with the Earth's rotation, and the stars appear unchanged, as if frozen in place. This illusion of stillness is just that, a mirage, a trick of scale. In reality, we are moving at incredible speeds, caught in the cosmic dance. And while the universe expands, stretching outward in all directions, the peaceful stillness of the sky remains unchanged. But what is this motion, and where is it taking us? For most of human history, we have seen ourselves at the center of it all, the universe revolving around us. That vision has been replaced by a new understanding, one that places us as just one tiny speck in an ever-expanding universe, forever in motion, traveling through space-time. In ancient times, the Earth was seen as the immovable center of the universe, but the mathematical model constructed by Claudius Ptolemy in the 2nd century CE solidified the Earth-centered view for over 1,000 years. Ptolemy's model was an intricate system of concentric spheres with Earth at the very center, surrounded by the moon, the planets, the stars, and beyond that, the heavens. This geocentric model explained the movements of celestial bodies, albeit with some complexity. It introduced the concept of epicycles, small circles that planets moved along while also orbiting the Earth to account for their backward motion in the sky. But despite the model's mathematical sophistication, it couldn't answer all the questions. Planets still exhibited strange behaviors, such as retrograde motion, which seemed to defy the circular orbits Ptolemy had proposed. As astronomers continued to track the planets, these anomalies became harder to ignore. Eventually, this model, no matter how meticulously refined, began to unravel. The truth was not to be found in a stationary Earth at the center of the universe. Enter Nicholas Copernicus. In 1543, he published his heliocentric model of the universe, placing the Sun at the center and suggesting that the Earth was just another planet, orbiting the Sun. This was a radical shift that would take decades to be fully accepted, as it directly challenged the established worldview. Copernicus's model explained the apparent retrograde motion of planets, but it still relied on the idea of circular orbits, which would later be proven incorrect by Kepler. The next pivotal moment came with Galileo Galilei's invention of the telescope. In 1609, he turned his telescope toward the heavens and saw things that shattered the old model. he observed that the moon was not a perfect, smooth sphere, but one pockmarked with craters. He saw Jupiter's moons orbiting around it, proving that not everything in the cosmos revolved around the Earth. Most dramatically, he observed the phases of Venus, which could only be explained if Venus were orbiting the Sun, not Earth. But while Galileo's discoveries were profound, it was Kepler's breakthrough in the early 17th century that provided the final blow to the ancient cosmic model. Using Tycho Brahe's incredibly precise data, Kepler revealed that planets do not orbit the Sun in perfect circles, as both Copernicus and Ptolemy had assumed. Instead, they followed elliptical paths. This revelation would go on to become one of the cornerstones of modern astronomy, and Kepler's laws of planetary motion are still used today to predict the orbits of planets, moons, and artificial satellites. However, even though Kepler and Galileo had radically changed our understanding of the cosmos, the Sun still seemed like a fixed point in the vast, endless void of space. It wasn't until the work of William Herschel in the late 18th century that we first began to think of our solar system as part of a much larger structure. Herschel, a composer turned astronomer, turned his telescopes toward the stars, attempting to map their positions and count their numbers. He was the first to realize that the stars were not scattered randomly but formed patterns, galaxies of sorts, within a cosmic structure. His model of a galactic system, though later proven incorrect, marked the first step in the discovery of the true scale of the universe. But it wasn't until Edwin Hubble's groundbreaking work in the early 20th century that the true nature of the cosmos began to come into focus. Hubble's observations of galaxies, especially his discovery that Andromeda was far beyond the Milky Way, proved once and for all that the universe was far larger than we had ever imagined. His work showed that galaxies were not just stars, but entire collections of stars, and these galaxies were moving away from each other, an observation that led to the formulation of Hubble's law, which states that galaxies are receding from us at a rate proportional to their distance. The implications were staggering. The universe, it seemed, was expanding. This realization laid the groundwork for the Big Bang theory, which posited that the universe had begun from an incredibly dense and hot state and had been expanding ever since. The discovery that the universe was not static but dynamic set the stage for a new era of cosmology, one that would eventually lead to the discovery of dark matter and dark energy, two forces that make up the vast majority of the universe yet remain mysterious and invisible. As the 20th century unfolded, astronomers were no longer questioning whether the universe was expanding, but how and why it was doing so. The universe, it seemed, had been expanding ever since the Big Bang. The realization that galaxies were not static, but were moving away from one another, challenged everything humans thought they knew about the cosmos. The pursuit of understanding this vast expansion led to some of the most profound discoveries in modern science. But as scientists dug deeper into this mystery, they encountered an even more mind-bending question. What is driving the universe's expansion? What force, unseen and powerful, was stretching the fabric of space itself, pushing galaxies farther apart? In the early 20th century, the idea of a static universe was still held by many, including Albert Einstein. When he first formulated his theory of general relativity, he believed that the universe was unchanging, a cosmological constant that would never grow or shrink. But when the evidence for the expanding universe mounted, Einstein was forced to accept a new reality. His theories no longer held, and even he was astonished by the implications. It was astronomer Edwin Hubble who in 1929 made a landmark discovery that would change our perception of the universe forever. By observing the redshift in the light from distant galaxies, Hubble showed that galaxies are moving away from us in all directions, and their speed is proportional to their distance. The further away a galaxy is, the faster it is receding from us. This discovery became known as Hubble's law, and it provided solid evidence that the universe was not static, but expanding. But the question of what was driving this expansion remained unanswered. What was the force behind the stretching of space itself? The idea of an invisible force seemed almost absurd. After all, Forces in the universe are typically associated with matter, things we can see, feel, and measure. Yet the expansion of the universe appeared to defy this basic rule. Then, in 1998, a startling discovery added a new layer of mystery to this already perplexing question. Two independent teams of astronomers studying distant supernovae found that not only was the universe expanding, but it was doing so at an accelerating rate. This was entirely unexpected. The gravitational pull of matter should have slowed down the expansion over time. Instead, something was causing galaxies to move away from each other at an increasingly rapid pace. This new phenomenon became known as dark energy. It was an elusive and unknown force that seemed to work in opposition to gravity, pushing the fabric of space apart instead of pulling it together. While dark energy made up about 68% of the universe, it was as mysterious as it was powerful. Scientists had no idea what it was or how to even begin studying it. All they knew was that it was driving the universe's expansion and that it would eventually lead to the galaxies becoming more and more isolated from each other. The discovery of dark energy raised the stakes of the cosmic mystery even higher. Not only was the universe expanding, but it was expanding faster and faster, with no clear explanation for why this was happening. It was a puzzle with no easy answers. As scientists began to study the implications of dark energy, they turned to the fundamental principles of physics. They explored the fabric of space-time itself, trying to understand how the universe could stretch and bend in the way that it does. They discovered that the very nature of space-time is not static, it is flexible and dynamic. The expansion of the universe is not like an explosion from a single point, it is a continuous stretching of space itself. But if space itself could stretch, could it also fold? Could there be regions of space where the fabric itself warps, creating realms where the laws of physics no longer apply in the same way? Theoretical physicists began to explore these questions in earnest, positing the existence of wormholes, hypothetical passages through space-time that could connect distant parts of the universe. But even with the idea of wormholes, one question remained. Where is everything going? The galaxies are speeding away from each other, but to what end? Are they destined to continue this unrelenting journey into the void, with the universe expanding into an endless emptiness? Will galaxies eventually drift apart so far that they are no longer visible from one another, forever isolated in their own cosmic regions? The answer to this question is still uncertain, but there are two primary possibilities. One is known as the Big Freeze, in which the universe continues to expand at an accelerating rate, pushing galaxies farther and farther apart. In this scenario, the universe would eventually become cold and dark, with stars burning out and galaxies moving beyond the observable horizon. Over trillions of years, the universe would become a barren, empty expanse, with no traces of the cosmic activity that once existed. The second possibility is the Big Rip. In this scenario, dark energy becomes stronger over time, eventually reaching a point where it tears apart everything in the universe, from galaxies to stars, planets, and even atoms. The Big Rip would be a violent, apocalyptic end to the universe, where space itself tears apart, undoing the very fabric of reality. While these scenarios may sound fantastical, they are based on current observations and theoretical models. The truth is that we are still a long way from understanding the full nature of dark energy and the ultimate fate of the universe. Some scientists even speculate that there may be a third possibility, a more subtle scenario in which the universe reaches a stable but ever-expanding state, where galaxies continue to drift apart, but without the catastrophic events of the Big Rip or the cold death of the Big Freeze. However, despite these theories, one thing remains clear. The universe is not static. It is not a closed, fixed entity, but an ever-evolving, ever-expanding cosmic landscape. Everything we observe, from the motion of galaxies to the behavior of light and matter, is a result of the stretching of space-time itself. As we continue to explore the universe and observe its distant corners, the question of where everything is going remains unanswered, but the journey itself is undeniably awe-inspiring. The universe is not merely a collection of stars and galaxies. It is a living, breathing entity, forever in motion, pushing the limits of human understanding. And as long as we continue to look up at the stars, we will remain on the front lines of this cosmic adventure, seeking answers, expanding our knowledge, and contemplating our place in the vast, expanding universe. But the most profound realization of all is that even as we seek to understand where everything is going, we may never truly know where it ends. The only certainty is that the universe will continue, ever expanding, ever changing, a testament to the vast mysteries that still await us. As we continue to delve into the vastness of the universe, another question arises. What happens to the structure of the universe as it expands? What forces are at play behind the scenes that cause this perpetual stretching of space-time? More importantly, as the universe pushes outward, is there an ultimate limit to this expansion? Or will it continue infinitely, a cosmic dance that never ceases, forever reshaping the very fabric of reality? Scientists have long pondered the nature of the universe's expansion. In the early 20th century, the discovery of the redshift, the phenomenon by which light from distant galaxies appears stretched, moving toward the red end of the spectrum, was a crucial indicator that the universe is expanding. This observation, made by Edwin Hubble in 1929, marked a significant turning point in our understanding of the cosmos. It was a moment that set the stage for everything we know about the universe's origin and eventual fate. Hubble's law revealed that galaxies are moving away from us, and the farther they are, the faster they recede. This led to the realization that the universe itself was stretching, pulling everything apart as it grew. This expansion, however, wasn't just about galaxies getting farther from one another. It was about the very space between them stretching, and that stretching process would continue indefinitely as long as the conditions remained the same. But in recent decades, a new revelation has sent shockwaves through the scientific community. The expansion of the universe is accelerating. This was a discovery made in the late 1990s by two teams of astronomers studying the light from distant supernovae. What they found was astonishing. The universe's expansion, which was once thought to be slowing down due to the pull of gravity, is actually speeding up. How is this possible? The answer, or rather the mystery, lies in a force that is pushing the universe apart: dark energy. Dark energy is an enigmatic force that makes up approximately 68% of the universe's total energy density. Despite its overwhelming presence, dark energy remains one of the greatest unsolved puzzles in modern physics. It appears to be a repulsive force, working against gravity to accelerate the expansion of the universe. But beyond this basic observation, little is known about its true nature. What we do know, however, is that dark energy seems to be a fundamental part of the universe's fabric. It is responsible for pushing galaxies apart, preventing them from collapsing inward due to gravity. And as the universe continues to expand, dark energy becomes an even more dominant force, dictating the future of the cosmos. As dark energy accelerates the expansion of the universe's structure also undergoes dramatic changes. Galaxies that were once gravitationally bound to one another are now drifting apart. Superclusters, large groups of galaxies bound by gravity, are being stretched and separated. And as the distances between galaxies increase, the universe will become a darker and emptier place. Over billions of years, stars will burn out, galaxies will become isolated, and the universe will be left with only the faintest remnants of its once vibrant past. But while this cosmic isolation seems like a somber conclusion, it's important to recognize the scale of time involved. The timeline for these changes spans billions of years. In the early stages of the universe's life, galaxies were much closer to one another. The first stars ignited, giving birth to galaxies, and those galaxies began to collide and merge, forming even larger structures. But now, as the universe ages, the the grand-scale collisions and mergers between galaxies are becoming increasingly rare. What does this mean for our own galaxy, the Milky Way? As the universe expands, the Milky Way will continue to move through space. In about 4.5 billion years, the Milky Way will collide with our neighboring galaxy, the Andromeda Galaxy. This collision will be a massive event, a cosmic dance between two galaxies that will ultimately result in the formation of a new, larger galaxy. But this process will not be quick. It will take billions of years, with stars and gas clouds merging, and only a few stars being close enough to collide with one another. For the most part, the stars in both galaxies will simply pass by each other. The merger of the Milky Way and Andromeda will lead to the formation of a new galaxy, often referred to as Milkomeda or Milkomeda, depending on the eventual shape of the new galaxy. This new galaxy will be a spectacular sight, a massive, bright, elliptical galaxy formed from the ashes of two spirals. But even after the merger, the universe will continue to expand, pulling even the newly formed galaxy apart from the rest of the cosmos. One of the most intriguing possibilities about the end of the universe is that dark energy might not remain constant. If it does change, it could result in the Big Rip, a catastrophic event in which dark energy's influence becomes so powerful that it overwhelms all forces, including gravity. The universe would be torn apart, star by star, galaxy by galaxy, until all matter is stretched beyond recognition. This potential end, one of endless stretching, tearing, and fracturing, raises profound philosophical questions. What does it mean for the universe to end? Is it the inevitable result of cosmic laws, or is it a consequence of a force we do not yet understand? As humans, we are in a brief moment of cosmic history, a moment when the universe is still young enough for us to observe its wonders and mysteries, but not long enough to see its ultimate fate. The universe, in its vastness and complexity, has provided us with incredible insights into the nature of space, time, and the forces that shape everything we know. Yet, with each answer we find, we are confronted with more questions. The more we learn about the universe's structure, the more it feels like we are only scratching the surface of a deeper, more mysterious truth. As we continue to explore and understand the universe, we are reminded of the delicate balance that defines our existence. We are not the center of the universe. We are not even the center of our galaxy. But we are part of this grand cosmic story, and that alone makes the search for knowledge worth pursuing. The edge of the universe may never be reached. Its boundaries may be forever shifting, forever just out of reach. But in this search, in this unyielding pursuit of understanding, we will continue to push the limits of human knowledge and explore the vast unknown. As we journey further into the cosmos, one of the most profound realizations to emerge from modern astronomy is that the universe does not behave according to our expectations. It is not simply a collection of static objects scattered across an empty void. The more we study it, the more we realize that the universe is a living, breathing entity, constantly evolving, expanding, and interacting with itself in ways that were once unimaginable. It is in this context that we must confront another of the most profound questions in cosmology. What role do black holes play in shaping the universe? Black holes are no longer just exotic anomalies. They are integral components of the cosmos. These mysterious, powerful objects, once thought to be theoretical, have now been confirmed to exist, and they hold the key to understanding many of the most fundamental processes in the universe. When we think of black holes, we often imagine them as massive, dark entities that devour everything in their path. They are invisible, their gravity so intense that not even light can escape their pull. But this image, while accurate in some respects, does not fully capture the complexity and significance of black holes. They are not simply objects of destruction. They are engines of creation and evolution. One of the most striking aspects of black holes is their relationship with galaxies. It is now understood that nearly every large galaxy in the universe has a supermassive black hole at its center. These black holes, which can be millions or even billions of times the mass of our Sun, are thought to play a crucial role in the formation and evolution of their host galaxies. The massive gravitational forces of a black hole can shape the entire galaxy, influencing the orbits of stars and the flow of gas and dust. In fact, some scientists believe that the growth of galaxies and the growth of supermassive black holes are intertwined, each feeding off the other in a cosmic dance that shapes the universe as a whole. The process begins in the accretion disk, the swirling disk of gas and dust that forms around a black hole as matter is drawn toward it. As material spirals inward, it heats up and emits immense amounts of radiation, including X-rays. This radiation, in turn, can affect the surrounding galaxy, heating up gas clouds and preventing new stars from forming. In this way, the growth of a supermassive black hole can regulate the star formation in its host galaxy, keeping it in a delicate balance between creation and destruction. But black holes are not just passive participants in this process. As matter falls into a black hole, it can be expelled in powerful jets of particles and radiation, shooting out from the poles of the black hole at nearly the speed of light. These jets can stretch across vast distances, extending far beyond the confines of the galaxy itself. In some cases, these jets can influence the evolution of entire galaxy clusters, affecting the distribution of matter across the universe. This incredible power to shape the cosmos comes with a dark side. As black holes grow, they can become cosmic behemoths, swallowing everything in their path. But even as they grow, they remain elusive. We cannot see a black hole directly. We can only observe its influence on its surroundings. We can see the stars that orbit around it, their paths warped by the immense gravity. We can detect the X-rays emitted by the accretion disk. But the black hole itself remains hidden, a silent force pulling everything into its depths. As scientists continue to study black holes, they have begun to uncover more about their mysterious behavior. One of the most puzzling discoveries is that black holes seem to defy the laws of physics in certain ways. At the heart of every black hole lies a singularity, a point of infinite density where the laws of space and time break down. Here, the fabric of space-time is warped to such an extreme that it becomes impossible to predict what will happen. Matter is crushed to an infinitesimally small point, and the very fabric of reality itself is torn apart. This paradoxical nature of black holes has led to some of the most exciting and unsettling questions in modern physics. If we could somehow enter a black hole, what would we experience? Would time slow down to a crawl as the gravity stretches the very fabric of space-time? Would we be stretched and compressed, our bodies turned into thin strands of matter, like the spaghetti-like material that is often used to describe the process of falling into a black hole? Or would we simply be erased from existence, the laws of physics collapsing entirely as we reach the event horizon? The event horizon, the point of no return, is one of the most fascinating features of a black hole. Once you pass this boundary, there is no coming back. Not even light can escape, and all information is lost to the outside world. For years, scientists believed that once something crossed the event horizon, it was gone forever. But more recent theories have suggested that perhaps the information isn't truly lost. Could it be that black holes store information in some form in their incredibly dense interiors? If this is true, it could have profound implications for our understanding of the universe and could lead to a deeper understanding of the nature of space-time itself. In addition to their role in the formation and evolution of galaxies, black holes also raise profound philosophical questions about the nature of reality itself. If black holes can warp space and time to such an extreme degree, what does this tell us about the fundamental nature of the universe? Are the laws of physics truly universal, or do they change depending on the region of space we inhabit? If black holes can destroy information, does this mean that there is a limit to what we can know about the universe? Are there boundaries to knowledge that even the most advanced science cannot breach? As we continue to explore the mysteries of black holes, one thing becomes clear. They are not just cosmic curiosities. They are the key to understanding the universe's most fundamental truths. They are not just destroyers. They are creators, shaping galaxies, regulating star formation, and influencing the evolution of the cosmos. And as we learn more about them, we may find that black holes are not only the most mysterious objects in the universe, but also the most crucial. The question of what happens inside a black hole remains unanswered. Perhaps it is a question that will never be answered, but even as we look for answers, we are confronted with a deeper, more existential mystery. How does the universe operate, and what is its true nature? The more we learn, the more we realize that the universe is not just a collection of stars and planets. It is a vast, interconnected web of forces, matter, and energy, all interacting in ways we are only beginning to understand. And at the heart of it all lies the black hole, the cosmic enigma that continues to challenge our understanding of reality, time, and space itself. As we venture deeper into the realm of black holes, we find ourselves at the intersection of the known and the unknown, where the limits of human understanding are tested and pushed to their absolute boundaries. It is in this domain, where space and time themselves seem to break down, that some of the most exciting and unsettling discoveries in modern science have been made. The concept of black holes has captivated both physicists and philosophers alike for decades. Their very existence challenges the most fundamental principles of our understanding of the universe. As we explore the mysteries surrounding them, we find that they are not only capable of distorting space-time, but are also capable of influencing the entire fabric of reality. The deeper we look, the more we realize that black holes might be far more complex and significant than we ever imagined. One of the most fascinating aspects of black holes is the accretion disk, the swirling disk of gas and dust that forms around them as they pull in matter. This disk is not just a passive collection of material. It is an active, dynamic system, one that is constantly in motion and constantly changing. As matter falls into the black hole, it begins to spiral inward, heating up to incredible temperatures and emitting intense radiation in the process. This radiation is what allows us to study black holes, even though we cannot see them directly. The material in the accretion disk is moving at incredible speeds, often reaching velocities that are a significant fraction of the speed of light. As the material spirals inward, it collides with other particles, generating immense amounts of energy. This process, known as relativistic jets, results in the ejection of matter and radiation at the poles of the black hole. These jets are incredibly powerful, extending for thousands of light years and are capable of affecting entire galaxies, pushing matter outward and influencing the cosmic landscape on a grand scale. In fact, some scientists believe that these jets play a crucial role in the growth and evolution of galaxies. As black holes devour matter, they not only shape the space around them, but also influence the development of stars and galaxies. By heating up gas clouds and preventing star formation in certain regions, black holes can regulate the rate at which new stars are born. This process, known as feedback, can determine the structure of a galaxy, influencing its size, shape, and the number of stars it contains. But even with all these discoveries, black holes remain deeply enigmatic. Despite decades of research, we still do not fully understand what happens inside a black hole. The event horizon, the point beyond which nothing can escape, remains one of the greatest mysteries of modern science. Once matter crosses this boundary, it is thought to be lost forever. But what happens to it inside the black hole? Does it get destroyed, or is it somehow preserved in a form we do not yet understand? One theory, known as the information paradox, suggests that the information about the matter that falls into a black hole is not lost, but is instead encoded in a way that we cannot currently detect. This theory raises profound questions about the nature of information itself and its relationship to space and time. If information is preserved inside a black hole, it would mean that the laws of physics are not violated, and the black hole's singularity is not truly a point of infinite density. Instead, it might be a gateway to an entirely new realm of physics, one that we have yet to comprehend: the search For answers to these questions has led scientists to propose a variety of new ideas and theories. One of the most promising is the concept of quantum gravity, a theoretical framework that seeks to unify general relativity, which governs the behavior of large objects like black holes, with quantum mechanics, which governs the behavior of particles at the smallest scales. If quantum gravity can be successfully developed, it could provide us with a deeper understanding of the nature of black holes, their singularities, and the behavior of matter and energy in the extreme conditions near a black hole. Another theory, the holographic principle, suggests that the information contained within a black hole could be encoded on its surface, much like a hologram. According to this idea, the universe itself might be a kind of holographic projection, with all the information in the universe stored on a two-dimensional surface, rather than in three-dimensional space. This theory, though still highly speculative, has the potential to completely transform our understanding of space, time, and reality. As scientists continue to study black holes, they are confronted with the realization that we are not simply studying isolated objects in space. Black holes are cosmic laboratories, places where the laws of physics as we know them break down, revealing new, unexpected phenomena. They are the key to understanding the fundamental nature of reality, and they may hold the answers to some of the most profound questions about the universe. But as we delve deeper into the mysteries of black holes, we are reminded of just how small and fragile our understanding of the cosmos truly is. Despite all of our technological advances, despite all the discoveries we have made, we are still just beginning to scratch the surface of the universe's deepest secrets. For now, black holes remain as they have always been, enigmatic, powerful, and elusive. But with every new discovery, we move closer to understanding their true nature, and in doing so, we move closer to unlocking the deepest mysteries of the universe. As we continue our journey through space, the search for answers will continue to drive us forward. The universe is vast, its mysteries deep, and black holes are at the heart of it all. They are the ultimate cosmic challenge, one that will continue to captivate and inspire us for generations to come. As the mysteries of black holes continue to deepen, new technologies and methods of observation are being developed to help scientists peer further into the darkness, attempting to unlock the secrets hidden within these enigmatic cosmic entities. The universe, it seems, is not only expanding outward in space, but expanding in our understanding as well, with each new discovery offering a tantalizing glimpse into a vast unknown. One of the most groundbreaking advancements in modern astronomy is the development of gravitational wave detectors. These devices, like the LIGO, Laser Interferometer Gravitational Wave Observatory, are specifically designed to detect ripples in space-time, gravitational waves, caused by extremely violent events such as the merging of black holes. For years, this phenomenon had been purely theoretical, predicted by Einstein's theory of general relativity. But in 2015, LIGO made history by detecting the first-ever gravitational wave signal, marking the beginning of a new era in our exploration of the universe. This discovery confirmed the existence of black hole mergers, events that were previously too distant and too faint to be observed directly. Gravitational waves are an entirely new way of seeing the universe, offering insight into cosmic events that are invisible to traditional telescopes. This new method of observation has already opened up new frontiers, allowing scientists to explore regions of space where no light can reach, where no ordinary instruments could ever hope to peer. The first, gravitational wave detection, came from the merger of two stellar mass black holes, each with a mass of several tens of solar masses. The waves from this collision propagated outward across the universe, traveling over 1 billion light-years before finally reaching Earth. When these waves hit LIGO's detectors, they caused a tiny, imperceptible shift in the distance between two mirrors placed several kilometers apart. This minuscule distortion, smaller than the width of a proton, was enough to confirm the existence of one of the most elusive and powerful phenomena in the cosmos. But this was only the beginning. Since that historic detection, LIGO has continued to detect more gravitational waves from black hole mergers, each one revealing new and surprising details about these cosmic giants. One of the most exciting revelations is the fact that black hole mergers may not be as rare as we once thought. In fact, some scientists now believe that black holes might be merging on a regular basis, potentially reshaping entire regions of spacetime as they do. Yet, even as our ability to detect these cosmic events has improved, we are still left with many unanswered questions. For example, the masses of the merging black holes continue to puzzle astronomers. Why are some black holes so massive, far larger than we thought possible? And what happens to the material that falls into these black holes? Does it get destroyed, or does it somehow transform into something we don't yet understand? Theories about what happens inside black holes have long been the subject of intense debate. Some physicists suggest that the singularity, the point at the very center of a black hole, represents a boundary where the laws of physics break down. At this point, space-time becomes infinitely warped, and matter is crushed to an infinitesimally small point. But this idea leads to a paradox. If all information about the matter that falls into a black hole is lost, how can we reconcile this with the laws of quantum mechanics, which state that information cannot be destroyed? This is known as the information paradox, and it remains one of the most pressing unsolved problems in theoretical physics. To resolve this paradox, scientists have proposed various solutions. One such idea is that the information might be stored on the event horizon, the boundary around a black hole, in a way that we cannot currently detect. Another theory, known as the holographic principle, suggests that the entire universe might be a projection of information stored on a two-dimensional surface, with black holes serving as windows into this deeper, hidden reality. While these theories are still speculative, they represent an exciting frontier in our understanding of the universe. Black holes, it seems, may hold the key to unlocking some of the deepest questions in physics, questions about the nature of time, space, and even reality itself. As we continue to study black holes, we are confronted with the possibility that they might play a much larger role in the structure of the universe than we ever imagined. Some scientists believe that black holes might be responsible for the formation of galaxies, acting as the cosmic engines that drive the creation and evolution of stars and planetary systems. The immense gravitational forces they generate could influence the motion of stars, shape the distribution of gas and dust, and even regulate the rate of star formation within their host galaxies. This idea has led to new research into the relationship between black holes and galaxies. For example, astronomers have discovered that the mass of the black hole at the center of a galaxy is directly related to the size and structure of the galaxy itself. This suggests that black holes and galaxies may be intimately linked, evolving together over cosmic time. But what about the future? Will black holes continue to play a pivotal role in the evolution of the universe, or will their influence eventually fade as the universe expands and grows colder? As we look toward the distant future, we are faced with another profound question. What will happen to the black holes themselves? Some scientists believe that over trillions of years, black holes may eventually evaporate due to a process called Hawking radiation. According to this theory, black holes gradually lose mass over time, emitting radiation in the form of particles. This process is incredibly slow, but over immense timescales, it could lead to the eventual disappearance of even the most massive black holes. But this is still just theory. In reality, the fate of black holes is shrouded in uncertainty. Could they continue to grow indefinitely, devouring everything in their path until they dominate the universe? Or could they reach a point where they are no longer able to consume new material, slowly shrinking and fading away into nothingness? The answers to these questions may lie in the distant future, but for now, we are left to wonder. The more we learn about black holes, the more we realize that the universe is not just a static, lifeless expanse. It is a dynamic, ever-changing landscape, constantly shaped by the forces of gravity, time, and space. And at the heart of it all lies the black hole, a mysterious, powerful entity that continues to challenge our understanding of the cosmos. As we continue to unravel the mysteries of black holes, we must also consider the possibility that these enigmatic objects may hold secrets that extend far beyond their immediate surroundings. The deeper we delve into the cosmos, the more we realize that black holes are not just isolated phenomena. They are intricately woven into the very fabric of the universe. Their influence stretches across vast distances, shaping not only galaxies, but also the very nature of space-time itself. One of the most intriguing concepts in modern astrophysics is the idea of supermassive black holes. These behemoths, which can be millions or even billions of times the mass of our Sun, reside at the centers of most large galaxies, including our own Milky Way. But how did they come to be so massive? Could they have grown through the gradual accumulation of matter, or is there something more mysterious at play? Recent theories suggest that supermassive black holes may have formed early in the universe's history, possibly even before the first galaxies were born. This idea challenges our traditional understanding of cosmic evolution. If supermassive black holes existed at such an early stage, they must have been created through processes that we are only beginning to comprehend. One potential explanation for their formation is the concept of direct collapse. Instead of forming from the collapse of a massive star, as is the case with smaller black holes, supermassive black holes could have emerged from the collapse of vast gas clouds, never forming stars at all. These gas clouds, made primarily of hydrogen and helium, would have been incredibly dense, creating the perfect environment for the formation of a supermassive black hole. In this scenario, the collapse of these gas clouds would create a massive accretion disk, a swirling mass of gas and dust that would feed the growing black hole. This accretion process could have led to the rapid growth of supermassive black holes, allowing them to reach their enormous sizes in the early universe. However, this theory is still speculative, and more research is needed to confirm whether direct collapse could be the primary mechanism for the formation of supermassive black holes. Another fascinating aspect of black holes is their relationship with galaxy formation. As mentioned earlier, most large galaxies contain a supermassive black hole at their center, and the presence of these black holes seems to be closely linked to the growth and evolution of their host galaxies. But how exactly do black holes influence the formation of galaxies? One theory proposes that black holes may play a catalytic role in the process of galaxy formation. As matter falls into a black hole, it generates immense amounts of energy, which is released in the form of radiation and powerful jets of particles. This energy could heat up surrounding gas clouds, preventing them from cooling and collapsing to form new stars. In this way, black holes might act as a regulating force, controlling the rate of star formation in galaxies. But there's a twist. The energy emitted by black holes can also trigger new star formation in certain regions. In some cases, the intense radiation and particle jets emitted by a black hole can compress nearby gas clouds, triggering the birth of new stars. This feedback mechanism, where black holes both suppress and stimulate star formation, suggests that black holes are not just passive observers of galactic evolution. They are active participants, shaping the very structure of their host, galaxies. As we continue to explore the relationship between black holes and galaxies, we are confronted with the possibility that black holes may be the ultimate architects of the universe. They are not merely the endpoints of dying stars, they are the engines that drive the creation and destruction of galaxies. Their gravitational influence extends across vast distances, and their energy output can shape the evolution of entire galaxy clusters. But black holes are not just players in the cosmic drama of galaxy formation. They also hold the key to understanding some of the most fundamental questions in physics. As we continue to study these mysterious objects, we are forced to confront the limits of our understanding of space, time, and gravity. Black holes challenge everything we thought we knew about the universe, and in doing so, they force us to rethink the very nature of reality itself. One of the most mind-bending questions about black holes is what happens inside them. We know that the event horizon marks the point beyond which nothing can escape, not even light. But what lies beyond this boundary? What happens to the matter that falls into a black hole? And, perhaps most intriguingly, what happens to information? The concept of information has long been central to our understanding of the universe. According to quantum mechanics, information about the state of a system cannot be destroyed, only transformed. But if matter falls into a black hole, it seems to be lost forever, violating the principles of quantum mechanics. This paradox, known as the information paradox, has puzzled physicists for decades. One potential solution to the information paradox is the holographic principle, which suggests that the information contained within a black hole is not lost, but is instead encoded on its surface, the event horizon. This theory posits that the universe itself might be a hologram, with all the information about the cosmos stored on a two-dimensional surface. If this is true, then black holes may serve as gateways to this deeper, hidden layer of reality. Another theory, known as black hole complementarity, suggests that the information about matter falling into a black hole is preserved, but it is transformed in such a way that we cannot directly observe it. According to this idea, information is not lost but is encoded in the radiation emitted by the black hole as it evaporates. This theory is still highly speculative, and much more research is needed to determine whether it holds any truth. But the implications of these theories go beyond just understanding black holes. They could help us unlock some of the deepest mysteries of the universe itself, from the nature of space-time to the fundamental laws of physics. If we can solve the information paradox, it could revolutionize our understanding of reality, opening up new possibilities for exploration and discovery. As we continue our journey into the heart of the universe, we are reminded of the vastness and mystery that still lies beyond our reach. The universe is a place of wonder, awe, and discovery, but it is also a place of profound darkness and unknowns. Black holes are just one of the many enigmatic forces that shape the cosmos, and as we learn more about them, we gain new insights into the nature of the universe itself. The story of black holes is far from over. Each new discovery brings us one step closer to understanding the most fundamental questions about space, time, and existence. And as we continue to look into the darkness, we are reminded that the universe is not just a place to explore, it is a mystery to solve. As we come to the final chapter of our exploration into the depths of black holes, we are confronted with the truth that, despite the incredible advancements we've made in understanding these cosmic giants, there is still so much that remains hidden. Black holes have captured the imagination of scientists, philosophers, and dreamers alike for centuries. They are objects of immense power, seemingly able to bend the very fabric of space and time, yet they remain in many ways beyond our reach. Through our journey, we have discovered how black holes shape galaxies, influence the formation of stars, and even regulate the very structure of the universe itself. They are not just passive objects lurking in the void, they are active participants in the grand cosmic dance, affecting everything from the movement of stars to the evolution of entire galaxies. But perhaps the most intriguing aspect of black holes is their relationship with time. As we venture closer to these dark, mysterious objects, time itself begins to slow down. The closer we get to the event horizon, the point of no return, the more time appears to stretch and distort. For an observer falling into a black hole, the passage of time becomes disjointed, with seconds feeling like an eternity and the future unfolding before them in an ever-accelerating rush. It's a paradox, one that forces us to question everything we know about the nature of time and reality itself. At the heart of each black hole lies a singularity, a point where the laws of physics as we understand them break down. Here, space-time becomes infinitely warped, and the very concept of place and time loses meaning. What happens inside a black hole remains a profound mystery, one that we may never fully understand. But as we continue to push the boundaries of our knowledge, we inch closer to uncovering the secrets that lie within. Yet, even as we ponder the fate of matter and energy that falls into a black hole, we are forced to confront the unsettling realization that we may never be able to fully observe or comprehend the ultimate truth of black holes. These cosmic entities are both the key to understanding the universe and the greatest puzzle we have ever encountered. They are the boundaries of our knowledge, and beyond them lies the unknown. In the grand scheme of the universe, black holes represent the limits of human comprehension. They challenge everything we think we know about space, time, and existence. They force us to confront the very nature of reality, pushing the boundaries of science, philosophy, and imagination. And though we may never fully understand them, they will continue to drive our quest for knowledge, inspiring generations of scientists to look deeper into the cosmos. The story of black holes is not just about understanding one aspect of the universe. It is about exploring the very fabric of existence, the building blocks of reality itself. As we continue to investigate, we find that black holes may not only hold the answers to some of the greatest questions in cosmology, but may also be the key to unlocking even greater mysteries. They are the gateways to the unknown, the keepers of secrets that may forever elude us, yet continue to guide our journey through the cosmos. With each new discovery, we realize that the universe is far stranger, more complex, and more mysterious than we could have ever imagined. Black holes are just one piece of this grand unfolding puzzle. They are the cosmic enigma, the ultimate test of our scientific understanding, and the driving force behind many of our most profound questions. As we conclude this journey, we are left with more questions than answers. But perhaps that is the true beauty of black holes. They are not just objects to be understood. They are cosmic riddles, pushing us to expand the boundaries of our knowledge and imagination. They remind us that in the vastness of space, there is always more to discover, more to learn, and more to explore. And in the end, it is the pursuit of these mysteries that makes our journey through the universe so endlessly fascinating.